Good morning, everyone. So last time we went through the finite volume method applied on a staggered grid, and we talked about the different control volumes that we're going to be dealing with for the staggered grid. Again, the advantages of the staggered grid arises naturally from the integral formulation, allows us to conserve mass discretely very well. We're going to show that today. Today we're going to essentially focus on implementing what we derived last time. And we're going to start on the interior of the domain, and then we're going to look at what we're going to do at the boundaries. And if you remember, the boundaries were naturally easy for the velocities. So for the normal component of velocity, we just specify that directly at the boundary. For the tangential component of velocity at a given boundary, we specify the ghost cell. So essentially, you just invert the value on the interior to give you, on average, a desired value for the tangential velocity at the boundary. The pressure was a little bit more involved, but the idea is simple. You take the continuity equation and apply the conservation of mass at a cell near the boundary, and then you cancel or you set whichever velocity that is specified by the user. So if u at the boundary is 0, then you cancel that out from the discrete continuity at that cell. And then you replace each velocity with the projection form, so u tilde minus delta t grad p, and then you derive something for the pressure. But what that does, in effect, is you have one equation for the pressure, the Poisson equation, del squared p equal div u tilde over delta t, and just at the boundaries, you have to change the coefficients for that Poisson equation. So we're going to do that today. It's going to be a programming the staggered grid with finite volume can be nasty. So we're going to go with the brute force approach and I'll explain what that means. But we're going to do a brute force approach that's kind of the traditional way, using for loops, essentially, rather than slicing through arrays in Python. We're going to be doing for loops to enforce the integral formulation in your mind. So for the x momentum equation, we're going to loop over the x control volumes. Okay, and we're going to have to think about the indexing for those. And for each one of those control volumes, we're going to assemble the fluxes at the boundaries of the control volume and add them up together for a net contribution, okay? And then compute u tilde, right? That's what the projection is telling us. Then we go to the y momentum equation. For the y momentum equation, we're going to loop over the y control volumes. We also have to think about the indexing in that case, but we're going to do all of this on the interior. And the boundaries we would have already set, and then the second focus is going to be on the pressure. So there are a couple of ways we're going to construct the pressure equation. We're going to do a naive implementation for the successive over-relaxation, which is going to be very expensive. And then I'm going to show you just my results with a sparse linear solver, which is like a fraction of the cost of a standard linear solver. But we're going to learn about that later in the course, doing these linear solvers, okay? So just to remind you, for the x momentum equation, this is what we had. Now remember, we're first integrating u tilde, which is the momentum equation without the pressure gradient, okay? So this is the integral formulation for u tilde, d by dt integral over a u control volume. So that's a u control volume for u tilde. And u and u tilde live at the same location. V and v tilde live at the same location. And this is what we had. So the integral over the volume is essentially u tilde delta x times delta y, right? That's the size of the control volume. And then you have the time derivative approximated as u tilde minus un over delta t. And then we had the convective fluxes, which was the net contribution of uu and vu across the surfaces of the u control volume. And then we had the diffusive fluxes. And remember, we approximated the derivatives for the diffusive flux using second order approximations, and the convective fluxes we use just averaging between the different cells. This indexing is true to the when we stagger to the minus side, and it's true in the Python array. So when I say here this is vi minus 1 j plus 1, That's saying I'm going to go to the array V, and I'm going to grab Vi minus 1, J plus 1. And the indexing is true to that. So that's what's so great about putting it this way. So if you, as we loop over the U control volume, so we're going to start with U11 and U12, U22, etc. For each control volume, we have ij, and then we're going to easily grab all of these variables from their respective arrays. That's what's the simplifying feature of this procedure. Then when you divide by delta x delta y over here, you're going to get UU east minus UU west over delta x, and then VU north minus VU south over delta y, etc. And you have a delta x squared, delta y squared over there. Okay. Same thing for the V control volume. This is what we had. Let me just kind of show it so that it will guide us through the process. So we're going to start by doing this, and then the next step we're going to go after the pressure. And in this case, we're going to loop over the scalar control volumes because the pressure lives at the cell centers. So there will be we're going to do it in a couple of ways to construct the coefficient matrix or the coefficients in this equation. We'll leave that to the end. So, but let's get started. I want you to open up your Jupyter notebook, and follow me. Okay. So I'm going to create a new Jupyter notebook. I'm going to bring in my fancy styling. Okay, and then just going to grab a bunch of import just a bunch of libraries, standard libraries, NumPy, Matplotlib inline, SVG for Matplotlib, so that we get high quality graphics, and Matplotlib, pyplot, SPLT, animation if you're going to do animation, and I'm going to import time to time our solution. Okay. All right. So let's first define a few things. We're going to start by defining nx and y, etc. So nx equal 32, ny I'm going to set it equal to nx. Nu, the kinematic viscosity, let's just do that at 0.01. Lx is 1, and Ly is 1. Those are the domain extents. Can you guys see in the back? Yeah? Jebin? Okay, I want you to follow through with me. If you are behind, just let me know. Tell me, pause for a second, please, okay? dx is Lx over nx. Now, this is different than the finite difference, where we had to do nx minus 1. Because in the finite difference, we specified the nodes. Here, we are specifying the intervals. So with the finite difference, we had 5 nodes. That means we had 4 intervals. Over here, we're saying we have 4 intervals, okay? In this case, we have 32 intervals, and the spacing for the interval is Lx over nx. Same thing, dy is Ly over ny. If we set out by assuming nx equal ny in our equations and delta x equal delta y, it will simplify the implementation significantly. But there's no need to do that, okay? Okay, and let's define our boundary conditions. Just specification. U top is, let's say, 2.0. And then the other ones, U bottom is 0.0, U left, or V left, sorry, V left equals 0.0, and V right equals 0.0. And so I'm assuming that all the normal velocity components, all normal velocity components are 0, so no inlets whatsoever, okay? So on the left boundary and the right boundary, U is 0, on the top and bottom, V is 0, but I'm going to allow a tangential velocity to allow the top wall to move, or if you want the bottom wall to move as well. Okay? So we'll keep that generalization. Okay? So let's now print our Reynolds number. Interesting things happen at a Reynolds number of 100 and higher for the driven cavity. Reynolds number is equal to U top times Lx over mu. Okay? And that we're going to also pick our delta t again. So Reynolds number. Now choose dt based on the advection, on the linear advection diffusion constraint. So dt is going to be the minimum of 1 over 4 times dx squared. If dx and dy were different, you would choose the minimum of the two, okay? Because you want the smallest scale, okay? So minimum of dx dy, okay? So dx squared over mu, right? And then 4 times mu over u plus, so what we had was u plus v squared, but in this case we just have u, so we're going to do over u top, okay? So that is going to give us delta t, dt equal dt, okay? Have you guys caught up with me? Do you need a minute to sink this in rather than, I mean, is it helpful for you to type it as I'm typing? Are you thinking about it, or are you just blindly typing it? Pardon me? Okay, so when that sometimes happens, please stop me, okay, so that you take a minute and let it sink in, okay? Because I want this to be beneficial. I don't want you to just type it and just copy naturally. And you know, try to do things differently. Like, you know, I know Mokbel chooses different variable names, so that's interesting. You know, try to do it the way you think about it, being guided by my thinking, okay? And if you have suggestions to do something better, let me know, okay? All right, we're all caught up here. So we're going to print this, Reynolds number 200. Pretty good. All right, so now let's initialize initialize variables. Okay, so now we have to agree on what we're going to do for our grid, okay? I'm going to choose to make all arrays and variables to be of the size of the grid plus ghost cells, so nx plus 2, ny plus 2, okay? I'm going to take this entire grid, and I'm going to, although some variables we're going to only be dealing with interiors, it just simplifies everything when we say, okay, everything is going to be the size of the full grid, and so when we're dealing with interior, we deal with interior. When we're dealing with ghost cells, we deal with ghost cells, okay? But this makes the indexing and the slicing interesting, as we're going to see a little bit later, okay? Okay, so let's go ahead and do that. Initialize variables. We consider a staggered grid to the minus side. C class notes, all variables, size, nx plus 2, ny plus 2, okay? So u is np dot zeros, ny plus 2, nx plus 2 because of the inverted indexing. And same thing for v, np dot zeros, and same thing for pressure, okay? So we've initialized all of these guys, okay? I am not going to store the solution. Well, maybe we can, but I'm not going to keep track of the solution, okay? Just for simplicity, okay? So now we can start with our time loop. Time loop, time integration. Okay. While, or, we can do until t end, or we can do a number of time steps. The nice thing about doing a range of time steps is that you can keep running the cell, and so let's say we do 100 time steps. You run the cell once, great. Then you run it again, it will give you another 100 time steps. If we go to a t end, every time, if you want to run it again, you have to go and change t end again. Okay, so let's just do a fixed number of time steps that we can keep running until a desired number of time steps. Okay. So for n in range, 0 to n steps. Okay, and what I'm going to do here is n steps equal 100, let's say. Right? Now, this is what I'm going to do here is going to be different than what we did before. Because I want to optimize things a little bit. In the past, we had to apply the boundary conditions to the initial condition, and then we do time advance and then apply boundary conditions again. What I'm going to do here, I'm going to change that order. I'm going to apply the boundary condition at the beginning of the time step. Why? Because by the end of the time step, un plus 1 needs to be divergence free with preset boundary conditions. So if I calculate un plus 1 and then apply boundary conditions and then take the dilatation, it's not going to be 0 because those boundary conditions are going to be dependent on the interior. And so that is going to mess things up. Okay? So what we're going to do, we're going to apply the boundary conditions at the beginning of the time step and do the projection so that at the end, we know that we're going to be divergence free. Okay? Now, as you converge your solution to steady state, it's not going to matter because then your boundary conditions are not going to change in the ghost cells anymore. Okay? All right. So let's do the left wall first. Left wall. So what did we have for the left wall? This is just terrible resolution. Let me see. Okay. So what did we have at the left wall? So we don't care about, so we're going to start with the left wall, u and v velocities. So first, for the u velocity, we don't care about any of these guys, right? We care about these guys. So what we want to take this entire range, or this entire range, because this one is not going to matter at all, okay? So we want I equal 1 and all of j for u, okay? So this is true indexing to Python. Okay, so this is I equal 1, right? So the first index is always 1. And all y's, we want to set those equal to 0, okay? It would help if I can have 2 different windows, but I don't. Okay. Okay, so for the left wall, we're going to do u all of j, 1, I equal 1, 0, 0. So this means I equal 1, all of j, u equal 0. Okay? So that's for the left wall. Okay? For the right wall, it's the opposite, where u all of j, but the last entry in I equals 0. Are you convinced? This is the last entry. So let's fit this slide over here and hide the navigator slide only. Okay, and how do you hide presenter notes? Okay. Okay, so on the right side, this is u n x minus 1 or u minus 1 for I, okay? Because we go, sorry, nx plus 2 minus 1, okay? Because we go from 0 to nx plus 1 in indexing. So I goes from 0 to nx plus 1. Rather than saying we want u at nx plus 1, we're just going to do minus 1. That gives us the array from the back. So I'm going to take this entire range, I equal minus 1 and all of j. on this one? That's 0. So the indexing goes to nx plus 1 and ny plus 1. 0 to nx plus 1 is plus 2 total, right? Yeah, yeah. But what's nice about Python with these circular indexing is you can just start indexing from the end, okay? So minus 1 is, so j, all of j, that's the semicolon here. And then minus 1, that's going to give us I, the last entry in I, okay? Now, for the top wall, okay, so first we're going to set boundary conditions on u. Okay, so now for the top wall, okay, this is going to be interesting. Okay, what are we going to have for the top wall? So the top wall, the u velocity, we said we wanted, it's moving at u top, correct? Okay, so what are we going to do? Average, which ones? So these guys, all of these yellow guys, right, with these guys. Okay? So in other words, the sum of these two over 2 is going to be u top. Or u ghost is 2u top minus u interior. Correct? And we're going to do this in one shot. Okay? So this is, in terms of indexing, this is j minus 1, all of I. Right? This entire row is j minus 1, but all of I. And this entire row is j minus 2, and all of I. Agreed? Okay. So top wall, u, we want minus 1 for j and all of I equal 2.0 times u top minus, oops, this should be minus 1. So this is the ghost cell. Minus the interior, which is u minus 2, all of I. It's going to add a calculation at the ghost cell, but we don't care about this. This is going to be insignificant. Okay? What about the bottom wall? So imagine we have a u bottom, like we had. Okay? So bottom wall. Then u ghost, what is the index for u ghost? 0 all of I. Yes. So j is 0 and all of I is equal 2 times u bottom, which is 0, minus, what is u interior? u1 all of I. Perfect. Now, set boundary conditions on V. Funny thing here is that the interesting thing is we can just swap the indexing, and you can get them all in one shot. But we're not going to do that. We're going to do them one at a time just to reinforce these ideas in our mind. Okay? So we'll start with the top wall because it's a normal velocity. Top wall, what do we do at the top wall for V? Okay, but what's the indexing? All I, yes. So V minus j is minus 1, and all of I is equal to 0.0. Now, bottom wall, what is V at the bottom wall? Yes. So not 0, because 0 is the ghost cell. We don't care about that. J in terms of j. So j is equal to 1. So Vj equal 1, all of I equals 0.0. Now the left wall, what is going to be V? So V is 0 at the left wall, or V left. We have a V left. Let's assume we have a V left. So what are we trying to set at the left wall? Yes. So the average of this entire column for V's and this entire column. So how do we think about this? We're averaging over all j between two values of I. I is 0 and I is 1. So I is 0 for the ghost cell. We're setting that for all j. Okay, so v all j I equals 0 is equal to 2 times v left minus v of the interior, which is all j I equal 1. Okay? So v, we set for all j and I equals 0 is equal to 2 times v left minus v interior, which is v all of j and I equal 1. Right wall is the same thing, but we're going to go to the end. So v all of j minus 1 for I, right? So this is these v's over here, right? All of these v's. So I is minus 1. So all of these v's. I is minus 1, and this I is minus 2. Okay? So minus 2. Right one. Great. We're done with boundary conditions. And we can clean this up a little bit if you want, so that you don't clutter your code. Sometimes comments get in the way. Your OCD, you want to align things perfectly. Oops. Okay. Okay, now we can start calculating U tilde. Okay? We're going to compute or assemble. So in some circles, at least where I did my master's, in the Patankar school of thought, they call this assemble the momentum right-hand sides. Okay? So we're going to assemble everything. And typically the word assemble comes from implicit methods, where you end up with a matrix assembly algorithm. We're not doing implicit methods here, but we're going to assemble still the all the entries in the right-hand side for the momentum equation. So assemble x momentum first for, let's see, can I do tilde? Probably not. For U tilde, okay? And do interior points only. Okay, so what we haven't created is an array for U tilde. And we haven't said anything about the boundary conditions for U tilde, actually. Now, as I mentioned in the past, there are two ways of thinking about U tilde. You could say that at a velocity boundary, you know the velocity, so you don't need a correction. So U is equal to U tilde, but that enforces a pressure gradient equal to 0. Remember the Helmholtz decomposition. That's one way of approaching it. We're not doing this in this case, because we're not assuming that at the boundary. We're deriving a condition for the pressure different. That's not obviously dP by dx equals 0. It's going to give you a more natural pressure gradient. But we haven't said anything about U tilde. As far as we're concerned, U tilde is actually just 0. Because if you go back to when we applied the continuity equation for the pressure, when we eliminated that U component, and we ended up computing getting just a pressure gradient, so U tilde is really 0. There's no contribution for U tilde. So what we're going to do here, we're going to set an array. We haven't declared an array for U tilde yet. So So we're going to declare an array for u tilde, make it 0, but only touch the interior points so that we don't ever have to enforce the boundary condition on u tilde at all. It's always going to be 0. Same thing for v tilde. Okay? So let's go back and declare an array for u tilde. Okay? ut is the same. So u tilde and v tilde. Oops. So u tilde and v tilde. You know, it's not wrong. It makes physical sense to say there's no correction at a velocity boundary. Therefore, the pressure gradient is 0. You're going to encounter two issues there. The first issue is when you solve for the pressure with Newman conditions, you're going to have a hard time getting a unique solution if using direct methods. So you need to use like Krylov methods, and then still with Newman conditions, your pressure is going to float. And secondly, what is a true pressure at an inlet, for example? What is a pressure gradient at an inlet? Okay, if you have Newman 0 at an inlet, you know the velocity in Newman is 0, and so that's really sometimes doesn't make sense. But with this method, we may be able to actually compute a real pressure gradient because we haven't specified the pressure at the inlet. Really what's happening is we're just setting a velocity, and whatever pressure gradient that produces, we're going to take that. Okay? But both of them will produce correct velocity fields. Okay? Because the pressure, again, is like this. It's a parameter. With the projection method, at least, the pressure is not a physical quantity. P is just a parameter that allows you to enforce mass conservation. Okay? Okay, so now we set u tilde. We're going to assemble the, okay, what happened here? The momentum, the x momentum equations first. Okay, now like I said, I was going to do the brute force approach. And the brute force approach is going to entail looping over the u control volumes. Okay? Now, I want you to take note so that we think about the indexing that we're going to go through. So we're only looping over the yellow points. Okay? We said we don't care about the ghost cells. Okay? So we don't care about those. The boundaries are already set. I don't need to touch the boundaries. Okay? So I'm going to start from this one. So our I indexing starts from 2. Our I starts from 2. And then we're going to go all the way to this point. We're not going to touch that point. So it's going to go to an x, correct? Because this is an x plus 1. So 0, 1, 2, etc. to an x plus 1. So we're going to go from 2 to an x in I. Now in j, we're going to go from 1, this is the first interior point, all the way to this guy. So if this is 0, 1, ny plus 1, this is going to be ny. So in I, we're going to go from 2 to nx, and in j, we're going to go from 1 to ny. Okay? So that nested loop, I and then j, is just going to cover all of these interior points only. Agreed? Okay. So for I in range, we're going to start from 2. We said we want to go from 2 to nx. And because range is open-ended, so we're going to set nx plus 1 over here. Okay? So that gives us 2 to nx. If you're in doubt, just create a new cell and do for I in range 1 to 5 and see where it goes to if you forgot what range is going to produce for you. Okay? Now for j in range, remember we have a 2-dimensional grid. So we need to loop in I and j. For j in range, we said j is going to go from 1 to ny because range is open at the end. So we're going to do ny plus 1. Okay? Now ij is going to give us, so once we are inside the loop, we don't have to worry about what I and j are. So as far as we're concerned, this is a see the navigator. This is a uij cell, okay? As far as we're concerned, we're here, uij. So now we're going to assemble the different components of the fluxes. Okay, we're going to start with the convective flux, and we're going to do UU east, UU west, VU north, VU south, and that means computing all of these 6 guys. Okay, so let's zoom in on those guys. This is great because you can just you have IJ now, okay, and you can just copy these and put them in. Okay, so what do we have? Let's see if I can put them side to side. This is decent enough. Okay, U east. Now this is just a scalar. It's not an array. It's a number. Okay? So U east is going to be equal to 0.5 times U. We said J I plus 1. You don't have to worry about 0 indexing, non-zero indexing. You just implement these as is. Okay? Plus U I J. Okay? That's U east. U west is 0.5 times U Ji plus U J I minus 1. U north is 0.5 times U ij plus 1 plus U ij. U south is 0.5 times U ij plus U ij minus 1. So we wouldn't have been able to do this so cleanly if we didn't do this in the beginning. So, and remember, to do this, we started with the cell center, and we wrote the correct indexing, and we focused on a staggered volume, and then we calculated all the fluxes. That's how you do it. Spend your time, front load your effort. Okay? And sometimes we don't front load. We just we're excited, we want to implement something. And then we get stuck, and then we start spinning our wheels. Once you see yourself, you're wasting more than an hour on a thing that you thought was simple, go back to the basics and try to write everything that you need to do. Okay? Okay, so now we left at U south and U north. We still have V north and V south. Okay, those are Vn is 0.5. Now, do we have to worry about the indexing for the V array? No, because everything is relative to ij. We did everything relative to ij. Okay? So there's no ij for V or ij for P. Okay? So then we just grab Vi minus 1 j plus 1 from the V array. So that's Vj plus 1 I minus 1 plus V ij plus 1. So that's j plus 1 I. Okay? And that's V north. Vj plus 1 I. Okay? And then V south is 0.5 times Vi minus 1 j plus Vij. Agreed? Done. Done with the convective fluxes. That's the hardest one. And then convection is equal to minus U east times U east minus U west times U west over delta x, and minus U north times V north minus U south times V south over delta y. Okay? So if you look here, this is what we had. When we had a negative sign in front of it, and we divided by delta x, delta y. Okay? From the left-hand side. So that's convection. Diffusion is easy. And diffusion is simply nu times the Laplacian, okay? Nu times the Laplacian. Now remember, these are scalar values at the U control volume center. They're pointwise, okay? So they're not arrays. Mu times, what did we have? U I plus 1 j, so U I plus 1 minus 2 U I j plus U I j, U j, U I minus 1 j over dx squared, okay? Plus, in the y direction, the second derivative, U j plus 1 I minus 2.0 times U I j, so j I, plus U j minus 1 I over dy squared. Okay? Are you all caught up? Okay. I want you to think of it from these guys. Don't copy what I'm setting. Where are you doing the convective fluxes, Aaron? Still? Okay. Now dividing by dx dy is going to give us dx squared and dy squared. Okay? Yeah. Dx dy, right? So that gives us, that cancels out dy here and gives us dx squared, which is consistent with the del squared operator. But we got to it from the integral. All done? So my son says, Addu, Addu for all done. All right. Do you want to try doing the y momentum? And I'll walk around. Let's first, what should we do first before we implement the y momentum assembly, before we assemble the y momentum? Yes, so let's think about the indexing. What are we going to loop over? We don't want to loop over the ghost cells, so that eliminates 0 and 0 for I and j. We don't want the boundary, so that eliminates j equal 1, but we want to start at j equal 2, correct? So we start at j equal 2, and what is the upper limit for j? We're not going to get to the boundary, so that's ny plus 1. So we're going to go from 2 to ny. That's the limit. Those are the bounds on j. What are the bounds on I? We're going to do this one, that one, that one. We're going to skip the ghost cell. So on I, we're going to go from 2 to nx. Okay. In other words, your loop, you swap your loop for the, you swap the I and j limits for the for loop. Okay. So we're going to start, I is going to go from, I is going to be, yes, from 1 to nx, and j is going to be from 2 to n1. Okay? So once you do that, once you set the for loop, then I'm going to show you what we agreed on for the fluxes. Let me increase the size of these a little bit. Like 65 maybe, or 80. vertically. So that gives us nice equal OCD spacing. Okay. This is, oops, what we want to do for the Y momentum. Okay? Go ahead and try it. So we're going to do convection and diffusion. And convection, you need all of these 6 terms. The flux is at the faces of the control volume. Okay? Is this helpful for you? Okay, although but you're doing it in MATLAB. In Fortran. Okay, okay. Yeah, it's the same logic. Yeah, absolutely. So are you trying the implementation at home when you go home? Is it working for you? No. Yeah, it's hard plotting and yeah, I know. Yeah. That's why prototyping in Python first you learn in Python, then you go and do it in C or other complex languages. Be careful about copying and pasting from the U momentum because you're gonna be bound to make errors. Okay, Elizabeth. I know. It's just مقبل. Are we doing Jebel? Okay. Yeah.
How do you find an error in here when you mess up an index? Like, it seems impossible.
It is hard to figure out, but then if you suspect so what happens if you suspect your solution is not converging? What you do it on like a 4x4 grid, and you do it by hand, and you print you do one time step and print every single number, okay? And then if you have like 1 digit off, you know that's wrong. So now, hopefully by the end of class, we're gonna talk about um, complex visualization with Visit, and with Visit, it's even easier to detect bugs because you can kind of zoom in on a cell and look at the individual numbers and different quantities, okay? And there's a way to move data from Python to Visit, but it's just annoying. Um, okay, yeah, V south, V south. Continue. So when you combine convection and diffusion, this is a silly joke, like father jokes. You combine convection and diffusion, you get the confusion term. Or the convective and diffusive flux, it's the confusive flux. Good one. 7. Need help? So you need a new loop for the Y momentum, right? Yeah. See, the mistake you did when you copied is that these are actually V's, not U's.
Yeah.
Yeah. Yeah, don't forget to do those. That's the hard part, okay? How we doing? Okay, so I would leave it in the other form, and like I did here, because that enforces the idea that this is actually just a derivative. Okay, so this is really du dx and duu dx and dvu dy. Okay, so this will make it easier to catch bugs rather than assuming that your yeah. So the convective flux is minus duu dx, right? Minus dvu dy. So then you yes you do minus uu east or uv east u east v east. No, so that's still a minus. See. Yeah, so yes, this is confusion. So it's a negative sign in front of this guy. Okay, so if you put these two terms together, that's the derivative really of, yeah, if you look at the differential form of what is this term, it's really duv dx plus dvv dy. And then there's a minus sign in front of it. So you put the minus sign and you leave these guys as is. Okay? It's just something like this comes from experience. Like when you do it another way, when you get the negative sign all through and multiply it, you're bound to make an error. Okay? Okay. Good. Why? No, this is a local variable inside the for loop, and it's a pointwise variable. So you're wasting typing effort when you call it x and y. Same question that Mokba just asked me. No need to, because one, this is a local variable inside the for loop, and second, it's a pointwise variable that is going to be replaced every time. Okay? It's not an array that we're overwriting. Okay? Jabin, all caught up? Okay. Let's see. So then I'm going to copy my solution because you guys are all caught up. Okay, so let's see if I had it right. Okay, so this is what I have in what I had in my code for the y momentum. Had for I in range 1 to nx plus 1, which is going to give me I from 1 to nx, correct? And then j from 2 to ny, correct? And then v east, v west, u east, u west, v north, v south, and then convection. Oops. So in other words, Aaron, this is what we're doing here. It's minus duv dx minus dvv dy. Okay. Yeah. So putting it in this form kind of enforces this. Like, yes, this is really just a derivative, but in a finite volume sense. Okay. Now we forgot to do something. Now that we have convection and diffusion, we can just simply compute u tilde at the ij cell, correct? And v tilde. So what I'm going to do here is simply calculate u tilde at the ij cell is u at ij, okay, plus dt times convection plus diffusion. And you will see here, again, this is a side note, not intended to confuse you. People keep the convective term as du dx plus du dy and put a negative sign here and then say minus dt convection plus diffusion. Okay, so whichever one you like. But in chemical engineering, the fluxes are negative, right? They have a negative sign. in front of them for like diffusion, and then you have a negative sign in front of the entire flux, okay? So whichever one you choose, make sure you are consistent, okay? And then same thing for VT. VT is VJI, which is Vm, right? Plus dt convection plus diffusion. Okay, we are almost there. So now, obviously, this is not going to give us a divergence-free solution. Okay, we can try to run it, and it is not going to give us any. It's not going to give us a divergence-free solution. Okay, and we can actually plt dot quiver ut and vt, but I'm only going to do the interiors. Okay. Well, you can just do a quiver. It didn't do anything. It's just like when we did the finite difference case. If you remember, we did the finite difference case. Nothing. It didn't do anything. Okay. Well, okay, there's a mistake here. Not a mistake. It's not going to update because v and yes, v equal, so u equal ut dot copy, just to update, and v is equal vt dot copy, okay, just to update. Okay. Invalid value encountered in scalars. This doesn't make sense here. Did we get a nam? These guys are going to diverge. Okay, just taking a few time steps, it shows you that this is not a mass-conserving velocity field. Okay, just as expected. Okay, now we're going to focus on the pressure Poisson equation to make this guy divergence-free. But first, we need to do the pressure right-hand side. Compute pressure right-hand side, which is P right-hand side, I'm going to call it, which is 1 over dt times div u tilde, okay, div ut, okay? So what I'm going to do, I'm going to declare div ut to be an array and p dot zeros, or actually we can declare it outside. So let's put it outside. Div ut is np dot zeros, we can do like, zeros like u, okay, or p. So that's going to contain the dilatation of this velocity field that we just assembled, okay? Now, we can do this in either by looping over the cells and taking ut minus vt over delta x and ut. Yeah. I just declared an array for the dilatation of u tilde. So that's going to be on the right-hand side. Remember, this is this guy, div u tilde. Now we computed u tilde everywhere at the faces here. Now we're going to take their divergence and put it in the center and solve for the pressure. So div u tilde, we can compute it in two ways. Either do a for loop over the interior cells. So div u tilde, where does it live? Ask yourself first, where does div u tilde live? You have three options: cell center, x staggered, or y staggered. Cell center, why? Yeah, so think of you can think of it two ways. It's the right-hand side of the pressure. The pressure lives on the right, on the cell center, so you know that's a cell center quantity. But it's the divergence of the velocity field is the continuity equation, which is a cell-centered quantity, okay? So what we're going to do, so div u lives where p lives, okay? So div u goes from 0, 0 to an x plus 1 and y plus 1. And at each cell, we're going to do this, du dx plus dv dy. That's what's going to happen, okay? And the indexing just does it for us, okay? So we can do a for loop but we'd only need to do the interior. I don't care about the ghost cells. I don't care about the dilatation in the ghost cells. There's junk, could be junk in there. I don't care. Okay, so then I is going to go from 1 to nx, and j is going to go from 1 to ny. Okay, so we can do it this way with a for loop, since we're doing for loops. Okay, so for I in range 1 to nx plus 1, so that's going to give us 1 to nx, and for j in range 1 to ny plus 1. Okay, then div u t, what did we call it? Yes, div u tilde ij is equal. Now this indexing is true to the grid. So what does div u? Let me show you this cell. It's ui plus 1 minus, so u tilde I plus 1 minus u tilde I over delta x plus v tilde j plus 1 minus v tilde j over delta y. Agreed? Because we are at cell ij. That's what's so great about this indexing. Okay? So we have ut I plus 1 minus u tilde ij over delta x plus v tilde j plus 1 minus v tilde j over delta y. Now that's going to go into the pressure right-hand side. Okay? So I can do, instead of declaring div, let's just do p right-hand side. Okay? Just do a pressure right-hand side and simply say then p right-hand side is p right-hand side over delta t. So that should give us this. This gives us 1 over dt times div ut. Okay? Agreed? So rather than doing 2 arrays, div ut and pressure right-hand side, etc., let's just do 1 array. So now for the hardest part, and that's the pressure equation. Okay? That's the pressure equation. Now, if you remember last time, we said this pressure equation holds everywhere at all points except at the boundary. Because at the boundary, what happens, some of the terms get eliminated. In other words, and specifically if you go and apply to the left and right and top and bottom boundaries, the coefficients of the pressures outside the domain are 0. And what do I mean by the coefficient of the pressure outside the domain? Well, if you think of the coefficient of Pij, it's minus 2 over delta x squared, minus 2 over delta y squared. The coefficient of Pi plus 1j is 1 over delta x squared. Okay? The coefficient of Pij plus 1 is 1 over delta y squared. Now, with respect to this cell, we can do the same nomenclature east, west, north, and south, and say the coefficient of the cell of ij, we call this AP, we're going to call it AP because that's the P cell, is minus 2 over delta x squared minus 2 over delta y squared. The coefficient of the east cell, that's A east, we're going to call this, just adopt a nomenclature. We're going to say this is A east, and what is that? That's going to be the coefficient of Pi plus 1, right? So that's 1 over delta x squared. A west is Pi, the coefficient of Pi minus 1. That's 1 over delta x squared. Okay. A north is the coefficient of j plus 1. And A south is the coefficient of j minus 1. Now, in practice, what this really implies is a matrix. Okay, is a matrix of equations, linear equations, because you're going to apply this equation at cell 0, cell 1, cell 2, cell 3. It's just going to give you a linear equation, and you have all of these coefficients in the matrix. But we're not doing matrices yet. We're just kind of inverting each point separately with the successive over relaxation. We say Pij is equal to this right-hand side minus everything else, and we keep iterating. But what's hard in this case, what's difficult in this case, is that the coefficients change as we approach the boundary. So as we approach the left boundary, as we saw last time, we knocked out P west, correct? Because there's no link to the outside at the left boundary. So if this is the left boundary, there's nothing outside. So P west, or Pi minus 1, doesn't exist. So we knocked out this term, but we also removed one coefficient here, 1 for Pij. Okay? Is that clear? Do you remember when we did this? So let me go back. Walls pressure, take the x minus side, apply continuity equation, See what happens here. P1j, it doesn't have a 2 over it. So P1j is the center coefficient in this case. It doesn't have a 2 over it because we knocked out one term, and we knocked out the term to P0j, the coefficient to P0j. But rather than thinking in terms of P0 and P1 and etc., think of a cell, okay? What are the pressure coefficients on that cell? You have a coefficient to the east, coefficient to the west, coefficient to the north, coefficient to the south. At boundaries, we're going to knock out the coefficients. Okay, for each coefficient we're going to knock out the coefficients that extend outside the boundary. So in a left boundary, we knock out the west coefficients. On the east boundary, on the plus side, we knock out the east coefficients. On the top boundary, we knock out the top coefficients. At the bottom boundary, we knock out the south coefficients. But we also have to clearly, correctly reduce the coefficient here. Now, if you do the math, we're going to eventually do this when we do linear systems and elliptic equations. There's a smarter way of figuring out the coefficient of the cell in the middle, okay, the coefficient for the pressure in the center. And you can show that the coefficient of the center is simply the sum of all neighboring coefficients. So in other words, if you have a cell, so here's how we're going to write things. You have a cell, Pij. We're going to do this as AP Pij, so that's the coefficient multiplying Pij, plus A east, P east, plus A west, P west, plus A north, P north, plus A south, P south. What is east, west, north, and south? They're relative to Pij, okay? But once we figure out these coefficients, they're either 1 over delta x squared, or 1 over delta y squared, or 0. If you are in the x direction, your coefficient is 1 over delta x squared. So east is 1 over delta x squared, and west is 1 over delta x squared. North is 1 over delta y squared, and south is 1 over delta y squared. And AP is simply the sum of all of the other coefficients, A east plus A south plus A west plus A north plus A south. Okay? So all we have to do is really set these coefficients correctly. What do we do at boundaries? On a left boundary, we knock out this guy, so left boundary. On a right boundary, we knock out this guy. On a top boundary, we knock out A north. And on a bottom boundary, we knock out A south. Now what happens at the corners? You knock out 2 of them, right? But it automatically does it for you if we do it in this way. So at a corner, for example, on a top corner, top left corner, what are the coefficients here? So A east is 1 over delta x squared, and then A west is 0, and then A north is 0, and then A south is 1 over delta y squared, and magically P is 1 over delta x minus 1 over delta x squared minus 1 over delta y squared. There's a negative sign. So what we're going to do to figure out the successive over-relaxation, what I'm going to do first is go and build these coefficients. Okay, and I'm first going to build them 1 over delta x squared and 1 over delta y squared, and then go at the boundaries, clean them up, and then add them together to create AP. Let me show you how I'm going to do it. I know this may have flown very quickly over you, but I really want to show you how we got there. Okay, so I'm going to create a new cell and do the Poisson solver in it. Okay. So first, I'm going to say build the pressure coefficients. In other words, this is a representation of the coefficient matrix. Okay. AP is going to contain all the coefficients for the center. Okay. Ny plus 2, and then nx plus 2. Okay. Now, A east is going to be 1 over delta x squared. Okay? Same thing for A west is 1 over delta x squared. And then A north is 1 over delta y squared. And then A south is 1 over delta y squared. Okay? Now, set the left wall coefficients. What happens at the left wall? A west, we're going to follow the same indexing as our grid. So at the left wall, I want to set the west coefficients of all of these guys. So remember, all of these guys, the west coefficient, I want to set that to 0. So I is going to be 1, and we're going to go over j from only on the interior from 1 to minus 1. Okay? So going a little bit fast here. So we're going to go from 1 to minus 1 in j, or you can go for the entire range in j. It doesn't really matter, because the outside coefficients are not going to matter. So we knock out the west coefficients on the left boundary, and then set the right wall coefficients. It's going to be the same thing, but A east. So A east for all of j at I equal minus 2. Why? So we are setting the east coefficients of these guys, the east coefficients. Okay? So, and these guys are minus 2 in I indexing, because this is minus 1. This entire range is minus 1. This is going to be minus 2. Okay? Minus 2 is 0. And then set the bottom wall coefficients. So that is going to give us A. So at the bottom, we want A south to be 0. So that's A south. And for the first interior cell, j is going to be equal to 1. J is equal to 1. And for I going from 1 to minus 1. Okay? 1 to minus 1 equals 0. And finally, set the top wall coefficients. So this is A south, and then A north, j minus 2 for the first interior, the last interior cell is j minus 2, and going I 1 to minus 1 equals 0. Now that gives us the structure of the east, west, north, south coefficients for each cell. All we need now is the coefficient of the pressure in the cell, and that's going to be just the sum of all of these. And this is where the magic happens. AP is simply minus A west plus A east plus A north plus A south. Okay? Now I'm going to use those coefficients to do the successive over relaxation, because once we have this, this is equal to Bij, right? Once you have this, the Gauss-Seidel, or the successive over relaxation, is simply says Pij is equal to Bij minus sum of A east, P east, okay, over AP. That's it. Now that we have the coefficients, we can just do this very quickly. Last time, or with the vorticity transport equation, we manually put in the coefficients. This is a more elegant way of doing it, that can handle boundary conditions more generally, okay? Now, I'm gonna just copy and paste the algorithm. It's identical to what we did in class. Okay, so I'm gonna call this pressure Poisson solver, or SOR, just SOR solver, okay? So same thing we did last time, except now I'm writing this in terms of the coefficients. And the successive over relaxation tells you that Pij is simply beta times this guy plus 1 minus beta Pij. That's it. That's the successive over relaxation. And what this is doing is looping over the interior cells. And for each interior cell, we're going to solve for P. And we're going to keep iterating until we converge, okay? I will give you the recipe for this, for the solver, so you don't have to worry about it. But what you have to worry about is figuring out these coefficients, okay? What they are. Okay, so now we are ready to just simply get a solution, okay? To simply get a solution. So what I'm going to do is say SOR solver. What? Oh, okay, didn't. On for dx unsupported types. Oh, MP dot ones. Not times. Okay. I'm gonna do SOR solver. Okay. What does the SOR solver need? It needs a pressure, which we initialized as 0. Pressure right hand side, dx and dy. Once we have the pressure, okay, once we have the pressure, all we do is a time advance. Final time advance. And that says that u, what we're going to do here is u tilde plus minus delta t dp dx, okay? But we're going to do this where? On the interior cells. I don't want to touch the boundary cells, because whatever is 0 in the boundary cells is going to be 0. Okay, so we're going to update. We're going to update. What are we going to loop over? I'm going to do this as a slice. Okay, we need this chunk over here. So in other words, x goes from 2 to minus 1, and j goes from 1 to minus 1 to give me these yellow guys. Okay, that's a slice. Okay, so u on the interior, final time advance, do interior only. I have 2 more minutes. So j 1 to minus 1, and then I from 2 to minus 1. Same thing, ut 1 to minus 1, I is 2 to minus 1, minus dt. Now, dp dx, what is dp dx? Remember, P is this entire matrix. Now, what we want dp dx over here on the interior. Okay, so this is this, so this guy minus this guy over delta x, and then, okay? So what we want really is this slice minus that slice. So all of these guys in P minus all of these guys in P over delta x. In other words, we start from 2 to minus 1, and then from 1 to minus 2. Okay? P, j, we're still on the interior, 1 to minus 1. But x is going to go from 2 to minus 1. So that's pi plus 1, okay, minus p, again, j is 1 to minus 1. And then I goes from 1 to minus 2 over dx. And for v, you just invert the indexing. I want to show you that this just is going to work. So that's what I'm trying to do here. So V is Vt, 2 to minus 1 minus delta t, and then we invert the indexing for P. And this is going to be a dy. And that's it. And if you had a timer, a time, or just t equals 0, we just increment t, say t plus equal dt. Okay, so let's run syntax error vt. Oh. Okay. Now u and v quiver. Look at that. We have something going on, but you see a mess up here. That's because of the ghost cells. So, but what I want to prove to you first is that the dilatation is 0. So how are we going to do the dilatation? We can do the same thing we did for the for loop over here. Compute dilatation. And I'm going to say div u is mp.zeros like p. And then we're going to loop over these guys. I'm going to say div u is simply u minus u and v minus v over delta y. And plt.imshow div u, plt.colorBar, div u origin equal bottom. Okay, where is the color bar? Okay, so it is showing some divergence, but 0.003. Now I claim that the error in the divergence is going to be equal to the error in the linear solver, because del squared p equal div u, right? And if your del squared p converges to 10 to the minus 3, then your div u is going to be 10 to the minus 3. So let's go and tighten the error in the linear solver. So we were only doing 100 iterations. I'm going to do like 1,000 iterations, and show you that we can tighten this all the way down to 10 to the minus 8 maybe. Okay, so let's run this again. It's going to take a lot of time because this solver is an inefficient solver. It's going to take time, a lot of time. And it's just 10 time steps. So this is actually a very good segue. Now see what happened here to our error. As we tighten the tolerance, okay, on our solver, but this error decreases, okay? But it's going to take a lot of iterations to get this to 10 to the minus 8. What I'm going to show you instead, and so this is a great segue for iterative solvers. What I'm going to show you is another implementation I did with a sparse linear solver, okay? So I'm going to take the same code, and I have a version of it on my laptop. Okay, so it is the same code that we did here, okay, same thing. But instead, I'm using, I am using a, what is it? Where are you? Bottom. See, sparse linear algebra, sparse solve, okay? So I have a sparse solver over here. Let me run this from the beginning. Okay, just a bunch of things that I've implemented. Okay, and I'm going to do, let's say, 100 time steps and see how fast. We did 10 time steps. It took us about 30 seconds. Okay, so I'm going to do over here 100 time steps, and it's done. It's actually just, well, still running. Should be done. And this is a 32 grid point. Oh, it's stuck somewhere else. It is stuck somewhere else, sorry. That's why it didn't finish. restart this. Okay, now it should be working. This is the way we did it in class, and this is the way we're going to do it next time with the sparse linear solver. This is the solver. It's done. See, it finished 100 time steps. But now check this out. Look at the dilatation, 10 to the minus 15. So not only we get the tolerance to machine precision, we get it like 100 times faster with an iterative solver, okay? And to prove to you that I have a driven cavity, so we'll do these next time. This is what we're getting. And you are enforcing mass conservation discretely at every cell with the staggered grid, okay? Whatever we did, even if we used a sparse solver with the finite difference case, there was no way we could drive mass conservation to 0, okay? Okay, this was a long lecture, a lot of coding. You'll have access to all the code. You can wrap your head around it, and you have the code on your laptops. I'll post the ones with the linear solver as well, but we're going to have a lot of opportunity to talk about linear solvers later in the class. Maybe we'll spend a lecture or two. Anyway, so next Tuesday, no class. Most of us are going to be out anyway. But on Thursday, next Thursday, we'll continue with this. And the Tuesday after, you can do your project presentations, okay? But next Thursday, your reports are due. So send me your reports, nicely typeset, preferably AIAA format, which you can find on Overleaf. Okay? Yes? Yes, upload, just send the code. I just need to make sure it works. Whatever parameters you put in there, just send me whatever with parameters that just run. And I just want to be able to run it to make sure that, you know, the work was done. Okay? How are the projects coming along? Interesting results? Are you getting interesting cases? I know Hong and Jebin were going to play around with the temperature at the boundary to effectively cool a person standing in the middle, maybe. Okay. Okay. Well, thank you. Have a nice weekend. I know that at the end it was a little bit, we went through quickly with the linear solver, but the essence is not the linear solver right here, okay? It is important. It is an important piece, okay, how you put it together. But we're going to have more opportunity to figure that out later on, okay? All right.